Welcome to CMA's lecture on transmission electron microscopy for material science. In this video, we will have a brief historical introduction about the transmission microscope and then review all the building parts of the instrument with which we will work during this lecture. The transmission electron microscope was first built by Knoll and Ruska in 1931. When they have built the first prototype. Actually, when they started working on this device, the idea was to prove as a theoretical demonstration that a thin electromagnetic coil would have exactly the same effect on electrons than a thin glass lens has on light. So if you want to prove this, the idea was to say, okay, let's prove that this lens, electromagnetic lens, can focus electron and make an image. And very soon they realized that it's possible to get images with better resolution than the light microscope. Only 2 years later, the transmission electron microscope is surpassing the light microscope in terms of resolution. And then only 6 years later, there are the first commercial instruments, which is quite fast if you look at the time and history in Germany at that time. And then time passes, and it's only in 1986 that Ernst Ruska is awarded the Nobel Prize. About the Nobel lecture, I really recommend that you have a read at the Nobel lecture by Ernst Ruska, because it's both very entertaining and very instructive on how this instrument was imaginated, developed, built, and all the interaction between engineering, technique and science at that time. I said 1933 the TEM surpassed the light microscope in resolution. Why is it so? How can we explain this? For the light microscope, you all know the Abbe diffraction limit based on the Rayleigh criterion. It gives you the smallest detail that you can resolve in a microscope as a function of the wavelength, lambda, and the numerical aperture n sinus theta. A similar formula holds for the electron microscope, where lambda is the wavelength of the electrons and theta the maximum angle at which electrons are collected. Let's try to plug in some numbers in there. Lambda for a typical transmission electron microscope at 200 kilovolt is about 2.5 picometer, 2 times 10 to the minus 12 meter at 200 kilovolt. Theta is the angle at which electrons are collected, and it's typically around 10 milliradians, say 10 to 20. So 10 to the minus 2 radians. You will come back later to this during the lecture. Okay, putting this into the formula, we get D approximately 1.2 times 2.5 10 to the minus 12 over 10 to the minus 2, which is around 3 10 to the minus 10. It's 3 angstrom. We are around the atomic distances in material. Atomic resolution is possible, and that was already recognized as early as in the 30s. Let's imagine now, if you improve things a little bit with lambda or with theta, then we can get maybe less than 3 angstrom. If we have 10 to 20 millirads, then 20 millirads gives us 1.5 angstrom. That's really around the interatomic distance in crystals. It's far above the resolution of a light microscope. And indeed, if we watch the evolution of the resolution of microscope, you see that the resolution of light microscopes was improving at the beginning and then is hitting some maximum, just limited by the Abbe diffraction limit and the wavelengths of light, and you reach something around 100 to 100 nanometers. And as soon as it started being commercialized, the electron microscope surpasses the resolution of light microscope and the resolution increase as progress is made to be able to work with larger theta or smaller lambda. But then it reaches also a maximum, which is just below 1 angstrom. Why is it so? Can't we improve things by having a very large theta? Well, actually not, because we have problems with aberrations. So these microscopes the resolution is limited by the aberrations and not, as for light microscope, by the wavelength. Later on, aberration-corrected microscopes were developed, and with an aberration-corrected transmission electron microscope, you can reach even better resolutions. So I think that's sufficient to be convinced that this is a fantastic instrument that will open an incredible amount of possibilities. But before learning how to work with it and how it works, we need to look at its different building blocks. So we need to look at all the constituents of the transmission microscope. Let's start with this microscope. It's a GEOL 200CX, an old generation microscope that has been cut open, so you can see all the internal parts, because normally they have to be under vacuum. The electrons are generated on the top and come down the electron column. They hit the specimen at the head of the specimen holder, and they are focused by all these electromagnetic lenses. So let's start from the top. We have the electron gun at the top. The electron gun will be the part that generates and accelerates the electrons. The first part, where the electrons are generated, is hidden behind this plastic part, and then all the ceramics are separating the different part of the accelerator. The emitter emits the electrons, and the accelerator stage accelerates them to the desired energy. There are 4 types of emitter listed in the next table. Tungsten and lanthanum hexaboride are so-called thermionic emitters. For those 2 types, the emitter is heated and the electrons are emitted because of this heating. The cold field emission gun is a real field emission emitter. The electrons are emitted thanks to a high electric field applied to the emitter. And in the middle we have the so-called Schottky FEG, which is a compromise between thermionic emitter and cold FEG, where the electrons are emitted by field emission assisted with the heating of the filament. A key quantity to characterize the emitter is the brightness. The brightness gives the intensity emitted per square meter and steradian. So if you take an area of your emitter and you look at the current, the number of electrons per unit of time emitted for this given area, and in a solid angle omega, you get the brightness. There's a huge difference in brightness between the different types of emitters, and a high brightness is linked to a high coherency because the electrons come from a small part of the emitter. This is important for phase contrast. A second characteristic is the size of the crossover after the emitter. It is much larger for tungsten than for the cold FEG. With a small size of the crossover after the gun, you will be able to focus your beam more precisely on the specimen, which will be good for chemical analysis, for example, or for working in scanning transmission electron microscopy. The third characteristic is the energy spread. How well are the electrons defined in energy? Field emission guns have a much narrower energy spread. This is both important for chemical analysis, but also a smaller energy spread gives a better temporal coherency, important for phase contrast as well. But those better characteristics come at a price. We need a higher vacuum for those emitters. which means that they are much more expensive in operation, but fortunately they also have a longer lifetime. Let's continue down the column to the next part, one of the most important one. It's the electron lens. The electron lens, you see some there, but also some down the column. They are electromagnetic coils. If you look at an enlarged picture where it's cut, you can clearly see how the wires, so it's just copper wires, winded around the optical axis of the microscope, and when they are cut, you see all these wires there. So with this geometry, they will generate definitively a field with a cylindrical symmetry. Also, with this type of lenses, there's a big difference compared to light microscopy. Here we can easily change continuously the focal length of the lens by just changing the current in the coil. And that is what we do all the time when we operate the microscope. For example, when we change magnification, the focus of the image, change from imaging to diffraction, etc. This is much more versatile than for light microscope. We had a little bit talk about this. They are bad lenses, so they have a lot of aberrations, and that will be the limiting factor to the resolution of microscope. So the TEM is limited by the aberration of this kind of lenses. That is why we will review the aberrations in the next lesson, as they are very important to understand the imaging properties of the microscope. Also, if you stick to lenses with cylindrical symmetry, as is usually the case in a transmission electron microscope, then you only get convergent lenses. And last, because the electron lens has the same focusing property on electrons than a glass lens has on light, you can make use of ray diagrams to understand your microscope as you do in light microscopy. So basically I have two news there. One bad news: the electron microscope is limited by the resolution of those lenses. But one good news: you will be able to use ray diagrams, and we will make use of them all the time during this lecture. They are very important to understand the working property of the transmission electron microscope. Okay, it's a good news, provided you remember how to use them. So, do you remember how to draw the image produced by a thin convergent lens? If not, it will be explained in the next video. But let's continue on the building parts of the microscope now. The next one that we will look at are the apertures. The apertures are holes of defined size placed on the path of the beam. They are supported by a thin plate mounted on a rod. You can see here some aperture in the lower part of the image also. These holes are small, 10 to 200 micrometers, and they will limit the extension of the beam. Generally, you have something like 4 to 8 sizes that you can choose from. Like here, for example, you recognize maybe 3 or 4 sizes, and they are at strategic places in the microscope. They will define some properties of the beam, like the one which is just after the beam forming coils that we will review next time, or the one which are at strategic places in the imaging parts of the microscope. And finally, we need to look at something, right? We want a specimen. We want the specimen held at some places. It's held in the goniometer and in a thing called the specimen holder. The specimen we look at in TM is small, and you will see that's the specimen holder that enters the beam. The optical axis is down there, and at that point you have the place for the specimen. So the specimen holder will hold the investigated specimen. Very commonly it's a 3 mm disc, and you need an area that will be transparent to your electrons. An order of magnitude is it should be around 100 nanometers or less. If it's thinner, it's much better for some imaging. Natively, you will be able to tilt your specimen along the axis of the specimen holder. That's what we call the alpha tilt. Some holder will also allow you to tilt the specimen along a second axis, which is perpendicular to it. And then some holders will allow incredible things, like you will be able to heat your specimen or cool your specimen to liquid nitrogen temperature or even to liquid helium temperature. You might be able to have electrical fields or electrical currents. You might be able to have some straining experiment or some indentation experiment. Well, there's no limit to the imagination. That will not be too much part of the lecture, but if you look into what's done in transmission electron microscopy, there's a huge variety of in situ experiments allowed by these specimen holders. And finally, to be a little bit back to the real world, well, I've brought you a specimen holder. It's there in its protective cover, and if I remove it, you see this very thin long rod. That's an O-ring that will allow to keep the vacuum in the microscope, and there you have the place where to put the specimen. So it's a small, thin disc, and some specimen can be, for example, nanoparticles or whatever that are deposited on a copper grid covered with a thin carbon film. How does the copper grid look like? Well, it's this very thin, tiny 3 mm disc that you have here. So manipulating them, you need a lot of care. So in this module, you have seen the main constituents of the transmission microscope. One of them is the lens. In the next module, we will review all the aberrations that are